So continuing on, we have the same beginning part of our script. We're creating our socket. We're going to connect over port 9000. Now this time we have an indicator before EIP gets overwritten. So we're going to put some A's there, and we're going to use that offset. Next, we're going to have 4 bytes that should give us the return address that we're going to need to use for the next iteration of this script. And then, of course, we're going to go ahead and send in that giant buffer. So really the changes here are we're trying to figure out what is the appropriate return address that we can actually point to and go to that return address first in front of our shellcode so that we can then have the stack execute our shellcode. So what we need to do is, if we go back to our crashed program here, we're going to restart that in Immunity. Okay, and then we're going to go ahead and hit play. And we're going to send in our modified script. Okay, and now we've come down. You can start to see on the stack here. You can see the parameter that was passed in to the program. So we're going to go ahead and step into this. We're at the top of our function again. Okay, well that was our mem copy. Let's go ahead and go towards the end before our return. Boom. So we crashed again. So now if we take a look at our stack here at the point where we've crashed, we can clearly see that, you know, EIP has been corrupted. So that's very sad. But what is really of interest to us is that we can see all of our A's. Remember how we added a bunch of A's and then we added those 4 bytes of B's, right? So and we can kind of see that's where the instruction pointer is pointing. What is really, though, of more interest is if we could make the instruction pointer actually point here, right? So this is the beginning of our buffer code, right? I don't actually want to call it shell code because it's kind of just buffer code. But this is the position really that we want EIP to be pointing to in order for it to then execute the shell code on the stack that we're going to send in just a moment. So what we need to do is go ahead and copy this address space 0022 F730. We can copy that to our Kali machine. And you can see that I have that here. So I'm basically having this added to our list of addresses. So the ESP at the top of our buffer is 0022 F730. Now we're going to use this as that good return address that I kept talking about, that we kept trying to find. And we're going to replace in our script the B's with this return address so that basically EIP points to that, and voila, our wonderful shellcode then gets executed. Now, the next step that we need to do before we actually modify our script is we need to actually generate some real shellcode that will allow us to do a TCP bind. Now, luckily, Metasploit to the rescue again. What we can do is we can actually use a tool in Metasploit Venom that allows us to create a Windows shell that would bind to TCP. So basically it will create a socket connection for us that can allow us to then connect with Netcat. So our platform is Windows, and we are going to create a shell bind TCP. We want the format to be C code, and our architecture that we're targeting is x86. Okay, so basically this is our good shellcode that's going to give us a TCP bind on port 4444. So what we want to do is we want to modify our script. I've created the next iteration of the script in smash me TCP bind. And here we've got our socket. We're connecting over port 90 over to our echo server. We've got our A's, which is fine. Now the next thing we can do is we want to replace those B's with the address that we found where we had the crash. Now if you'll notice the numbers here, and let me just minimize this so you can see, I've basically reversed the numbers, and this is due to the fact that Windows x86 is Little Endian, and if you don't know what that means, it's something to do with the way instructions are read by the CPU. I would recommend that you Google that and learn more about that. But basically what we have to do is we have to reverse these hex numbers so that the position or the memory location will be in the correct order when it goes to the stack. So we just reverse those. So I've got 0022F730. Okay. So, and then of course we've added in the shellcode that we just generated with our Metasploit tool. Okay, actually I added a no-op sled here so that we can make sure we slide into our shellcode. Shouldn't be a problem, but it's there just in case. And then we're going to send that over the wire. Okay, so then we go back to our Windows machine and we're going to restart the process. And now we are going to play. So the program is now running. Go back to our Kali machine, send in our exploit. We can step through again like we've done in the past, just to be consistent. Okay, so now we're about to come to that return. Aha! So our program has not crashed, so this is very good. And looks like we actually did come to the exact point, the return address that we wanted to come to, and that we set in our script. So this means, and here you can see those no-ops that we added. So that means that really this is the beginning of our shell code. We could actually verify this FC E882000000. If we go back to the Kali machine, we can see FC E882000000. Yep, that's our shell code. And that basically means that now I could go ahead and connect And as you can see, I am now connected to the Windows machine from the Kali attacker machine. And dir, etc. So this is the exploit of a buffer overflow using the dangerous function of memcopy. So in order to prevent the buffer overflow attacks from occurring like what we just saw in the last demo, processor manufacturers basically came up with a number of different countermeasures. Now these countermeasures are stack memory protections that are built into both the kernel as well as the compilers. And they include such things as canary values, dep and NX bit or no execute bits, and ASLR, and we're going to talk about each one. Now the canary values are basically values that are placed within a function before the function actually begins and then before it actually returns, that provide a mechanism for detecting if there's been any change to the return address, which, as we saw in the demo, was how we pretty much can point to our shellcode. So should these canary values change, it actually would cause an exception to be thrown, and the hardware would then basically segment fault your program from being able to execute that shellcode on the stack. So the dep or NX bit, and dep stands for Data Execution Prevention. NX, of course, is that non-executable bit. Essentially, what these are demarcations inside of memory that are specifically marked as non-executable. And should you try to actually execute on them, there would be a hardware level exception that would be thrown. Now, these types of protections are turned on by default now, say in the GNU compiler, and so anything 4.1 and greater is going to have NX bit turned on by default. So anything that you want to compile, you would have to explicitly turn this off if you did not want the non-executable bits set. Now ASLR is basically a memory randomization map that is turned on at the kernel level, and it is system-wide. Now for x86 Linux, we can easily see this by doing a cat on the randomized VA space and basically looking to see if it's set or not, and then you can actually disable it. Realize if you're running from a VM, which most of us probably are, that you can lose that setting upon your VM exit. So realize that it doesn't stick once you shut down that VM session. So just as I kind of mentioned, this slide goes into how you can turn off or disable these memory protection technologies. You can disable ASLR with the command that I provide there with the echo 0. And as I mentioned, if you're using VM, if you're using virtualization, that it is just temporary. You can also disable canaries and NX bits by taking by basically turning off that technique. When you go to compile your code, you can use a particular option that will turn that function off. So this next demo, I basically go into another classic buffer overflow, but this time on a Nihilum system, and I show how you can go ahead and disable these memory protection techniques in order to still achieve the same goal of smashing the stack.